Alrighty, good afternoon, folks. As everybody's piling in here, just want to welcome everybody to session three. Welcome if you're joining us for the first time. Welcome back if you have been here with us for sessions one and two. My name is Rachel. I am a program consultant with Geo. And before I turn this over to Michael, I'm just going to give a few rules of the road here. We are recording this session as always. We will be recording all of these sessions. We will be posting them both on Geo's YouTube channel and on the new website, which will be launching relatively soon here. We ask that everybody keep their camera and microphones off during this session. We will be taking Q&A at the end. But if you have any questions that come up in the middle of the session, feel free to put them in the chat for us. We will get to them at the end. Michael and our speakers have quite a few things that we're going to be going through today. So during the Q&A, we'll just have folks raise their hands or feel free to put your questions in that chat. And if you're having any technical difficulties, please email me. I will put my email address in the chat here as we get started. And before I turn this over to Michael, if everybody could post in the chat here where they are located in Ohio, we'd love to see which parts of the state we have represented here. And with that, Michael, I will turn it over to you.
All right. Good afternoon, everyone. Very nice to see you all online. This is session three on the microgrid series for municipalities, and session three is all about the technology. We're going to go relatively fast into this because there is so much to discuss. So, real quickly, Michael Benson, I'm the board president of Green Energy Ohio, also a distributed energy resource developer. And today is going to be all about the tech that you are wondering what it is that actually makes a microgrid go. There's a nice picture there. I'm not going to go down too much of this, but I do want to refer to it as it is new to us technology, but not new technology. And it will not be as surprising as you think. The best part is you're just going to be making your own energy, saving your own energy, controlling your own energy, and being able to do things that you didn't think you could do before, especially to support the electrification of your facilities, your fleets, your equipment and tools, things like that. So to get right into it, I'm going to introduce our speakers today. So first is up is Amy Simpkins as the co-founder and CEO at Mugrid Analytics. Amy Simpkins architects reliable, adaptive command and control for mission-critical distributed energy systems, aka microgrids. Mugrid provides bankable techno-economic analysis, optimized control, and project development of renewable energy, energy storage, and microgrids to maximize economic return, increase energy resilience, and promote energy equity in the U.S. and around the world. Amy is also the author of Spiral, a catalyst for innovation and expansion, and holds a master's degree in astronautical engineering from the University of Southern California and a bachelor's in aeronautics and astronautics from MIT. By the way, she is a literal rocket scientist. Before she got into microgrids, she worked on interplanetary travel. Our other guest is our other speaker is Justin Kale, the co-founder of Energility. He founded it in 2015 with his friend Craig, providing energy management services to nonprofits, small businesses, and commercial enterprise. They have conducted over 400 energy audits and supported over 300 projects, more than $85 million worth for their clients, reducing over 45,000 metric tons of carbon dioxide and saving more than $10 million annually. He focuses on helping real estate owners maximize their energy, environmental, and financial benefits, which, by the way, that's where the microgrids go, is on real estate. His background includes 15 years in commercial real estate, managing a high-rise tower and parking structure, and he also has 4+ years of experience consulting on energy efficiency projects for AMP Ohio's Energy Efficiency Smart Program. If those of you don't know, AMP Ohio is American Municipal Power. So if you are a municipal electrical system, that's AMP that supports those, especially those in Ohio. Justin holds a Counselor Real Estate Certified Energy Manager, and Systems Maintenance Technician designations. So, welcome, Amy and Justin. And what we're going to talk about, those of us who were on session one and session two, you will know that this is exactly it: resilient, grid connected microgrids. But now we're going to dig into the parts, the pieces, parts of all of this stuff, and how what you have at your facilities will be part of your electric grid, but also able to operate by itself for your security. So the components is the topic of today. And unless Amy or Justin have anything on this slide, I am going to move on and get out of the way.
Sounds good.
Great. Here's Amy.
So I wanted Michael to show that previous slide about resilient grid-connected microgrids first, just to establish terminology, right? To talk about that microgrids are collections of energy assets that generate energy, that store energy, and can serve local loads. So go ahead and go to the next slide. And the question is, what are those local loads? What is the kind of energy that we're talking about? And typically, when those of us who have come from a utility background or a buildings background, we're very focused on electricity, of serving the site with electricity. You know, solar and wind, after all, generates electrical energy. But we also use heat energy in buildings, at facilities. And it's really important. We're going to talk about a variety of technologies today that aren't only tied to electricity, electrical generation, electrical storage, but also to heat. And if you remember your middle school science, the law of the conservation of energy says that energy can't be created or destroyed, only converted into different forms. And so when we talk about generating or storing electricity, electrical energy, or we talk about generating or storing heat energy, it's important to remember that on some fundamental level of physics, they're the same thing. And it's always important. I always get worried about my clients who are in northern climes. I do work with some clients who are even further north than the snow belt in Ohio. And even though you guys are pretty cold right now, that I always want my clients to be thinking about heat and electricity at the same time. So between the last slide with terminology and this slide, these are to set the stage of saying like, hey, let's think about this in a really comprehensive way. And remember that if we draw the boundaries of our systems engineering around both electricity and heat, we can find more points of leverage and more efficiencies to take advantage of. So let's go to the next slide and talk about the topology of a microgrid. So typically, when we're talking about an electrical microgrid or heat microgrid, we've got kind of four different components. There is some kind of renewable generation component, and that allows you to be sustainable, of course, and have chemical-free generation, but also survivability, because your fuel source for a renewable source doesn't run out. Even if it gets dark at night, the sun will come back out again. Even if the wind dies down, the wind will pick back up again. And so when we are thinking about renewable types of generation, the usual suspects are sort of like solar and wind, but we can also talk about hydroelectric power or wave power. On the heat side, we can talk about geothermal energy. And then the second component of a microgrid is some sort of energy storage. And what energy storage does is it allows us to put non-dispatchable energy from renewable sources that just comes when it comes. And it allows us to put it at the time and in the place that we want it. So it offers us an element of control. In electricity, the most common component, the most common technology for energy storage is a chemical battery, like a lithium ion battery or a lead acid battery. But there are a lot of other types of energy storage, including mechanical flywheels or gravity storage, hydrogen and water electrolysis. There's also thermal types of storage where you can store heat for an amount of time and then deploy that heat later, either as heat energy to warm things or to generate electricity. The third component of this Venn diagram over here is what we call firm generation. And firm generation is also fossil fuel-based generation or any kind of fuel-based generation. And what this provides for us in the network, it is possible to have a microgrid with just renewable generation and energy storage. And it is also possible to have a microgrid with just fuel-based firm generation and not the other things to provide energy for your local loads. But in a multi-asset, multi-technology microgrid, the whole is greater than the sum of the parts. So firm generation or fuel-based generation can provide an element of reliability because you get to turn it on and fire it and activate generation whenever you need it, as opposed to the renewable generation that just comes when it comes, right? And then obviously there are downsides of firm generation, one of which is emissions, and the second of which is that it is based on fuel availability. And if you run out of fuel, Bob's your uncle, and that's the end. But and so what we do is we combine these three pieces of technology together in a microgrid to leverage their strengths together and allow their strengths to complement each other, to allow renewable generation to bring more survivability to firm generation, to allow firm generation to bring more efficiency to energy storage, and vice versa. And so the whole being greater than the sum of the parts, and now that we have multiple assets, we've introduced complexity to the system. And how do you manage complexity? You manage it with intelligent control. And that's the piece that's in the middle that ties it all together. Controls are usually a piece of software that's running on a computer that might be a combination of running locally there with the equipment or accessing the cloud for other data. But it's a really important piece. A lot of first timers will think that you can just buy some solar panels and buy a battery and wire them up together, and that's the end, and then it works. And they forget about, well, you need a brain to help you deliver the benefits of the microgrid. And so when we're doing design, and we're going to talk a little bit more about the design process in the next webinar session in a couple of weeks, the two questions are, how big should each of these elements be to appropriately work together and serve those local loads? And then how do you program those controls? How should each asset be operated together to achieve the benefits and the synergies between the assets? Next slide. So I'm going to hand it over to Justin for a minute to give you a great example of a microgrid system with these components.
Thanks, Amy. That was a great setting of the stage and getting us to a point where we can dig into a couple of examples that, as you alluded to, there's lots of moving parts here. And I was actually excited when Michael asked me to come and talk, because we do have a variety of clients from small business and nonprofits to larger commercial enterprises. And everybody's gotten to a point over the last decade where they're like, hey, how many times am I going to have to change my LED lights to reduce my electric load and become more efficient? And at some point, adopting renewable energy is a strategy. And whether it's for cost or for environmental reasons, we were connected with one of our clients that's a municipality. And their example here is they worked with us and with other experts, and we actually worked with Michael on this development project. They're in the process of discerning how to implement this, how to fund it. I know that's one of our series here in a couple weeks is about financing and contracts, et cetera. But with this community, they have a couple of the things that Amy talked about. They have a passionate person in finance that's also passionate environmentally, and she'd really like to get solar and battery. However, they also have EV charging stations. They have a police, fire, and administration building that are all connected together in public works and a campus. They also serve a disaggregated territory, so they have some park lighting and some other loads. So they have a bunch of different connected loads, but the consistency is they have a constant 24/7 load, and they're actually an Energy Star rated municipality, so they're managing the operations of their building very well, but they're looking to take the next step with their community, also serving low income and disadvantaged populations. They want to become a warming and a cooling center during those times that, as Amy pointed out, you have really heavy need to get rid of heat or to take on heat. And well, one of the ways that that can be done is through, microgrid, being able to kind of move the heat around through the different systems and being able to control it by bringing in the solar, bringing on the battery storage when it's necessary to manage the energy load. So this is just an example, and I'll turn it over to Amy as she takes us through some more of the nuts and bolts and details on the technology, but this is one example that may be applicable.
Awesome, thanks. Let's go to the next slide. So here's a big overview. And if you're saying, wow, there's a lot on this slide, you're right. And we're not going to necessarily go through each piece and talk about each of these technologies. What I want you to take away here is that there are a lot of options, and that many of these options can be combined and or controlled to work together in symbiosis so that the whole is greater than the sum of the parts, the way we just talked about in that topology cartoon diagram. And so this is kind of to give you a concept of what the flexible components are and what architectures can look like. So we're going to talk about each one of these categories. We're not really going to dive too far down into firm generation. The only thing I'll say about that before we move on here is that firm generation can cover traditional generators that you might think of, diesel generators or natural gas or propane generators. But there are generators out there that also accept alternative fuels or biofuels, plant-based fuels. There's also biodigesters. I'm a huge fan of the biodigester that takes literal crap from your wastewater treatment and is able to process it then into fuel that can be used to generate energy. To me, that's very circular economy and a great way to use fuel-based generation in that kind of a setup. And then the last thing I'll comment on the firm generation is to the original point that I made. There's a solution called combined heat and power, which actually is incredibly fuel efficient because it allows you to not only generate electricity from a fuel-based generator, but also take the heat offtake and use it. And so you get more bang for your buck about that. But we're going to start to walk through kind of each one of these categories and maybe talk about some of the details and talk about why it's important to consider them when you're looking at your microgrid. Next slide. So the first category we're going to talk about is the loads. And you might think, yeah, I know I've got loads. What does that have to do with microgrids other than it's, the reason for being? The thing is that many loads nowadays are able to be controlled. And so if we think of the microgrid not necessarily as a generation problem, but as a controls problem, loads are key parts of your microgrid because you get to decide to a certain extent when, how often your HVAC runs. This is why when there are high demands on the greater power grid, the utility grid, utilities can come out and ask people to turn their thermostats up so they're not running so hard on their air conditioning, right? They're asking you to adjust your load behavior in order to support the greater grid. The same is true for a microgrid. You can adjust either the timing or the distribution of your local loads in order to support supplying those loads on your microgrid. And so we have seen some pretty creative stuff done with HVAC scheduling and refrigeration scheduling. Lighting, plug loads, and communications are all pretty lightweight loads in terms of demand, but when you talk about IT, they're often really critical loads that absolutely have to have resilience. Industrial and manufacturing loads are both big and they're often voluntary and they have a direct economic impact on operations. And so you can really do trades between what is the energy costing me to run at this time versus what is the economic benefit I'm getting from those processes. Another one that is really cool is water purification and water treatment. We already talked about biodigesters. That's just one example. There is a term out there in the industry called the energy water nexus, because water purification and treatment, and in some cases desalination when you're next to the ocean, are very energy intensive processes. And so as we provide these absolutely critical services to communities, both water and electricity, they're actually very highly correlated, and we can do some cool things to have them interact together, again, in symbiosis. And then finally, the one that everyone typically thinks of right away is the EV charging, because often facilities are looking at bringing in microgrids or distributed energy resources at the same time they're thinking about electrifying vehicles or providing electrification infrastructure for community members. And so a lot of times that's already in the thought process. But EV charging, being such a nascent field as it is, also has a lot of opportunities for controllability. You know, how available does that charging need to be? Can the demand from that charging be distributed over a period of time, whether that's overnight or on a lunch break, or to make that demand a little bit less or a little bit more distributed to make it easier for our local generation to serve? So these are the questions we ask about loads. And a lot of these questions we can't answer, you know, our human minds can answer, and we can answer them in a strategy, in a qualitative narrative sort of way. But ultimately, there's computers, there's software that can help to calculate this, and that can help be aware of what's happening with the loads and how they're able to be scheduled, and simultaneously what's happening with the generation and how that power is available, and helping them work together. I'm going to say that over and over. That's if you take one thing away from this talk, it's about looking for ways to get these assets to work together in symbiosis and using controls to do it and to tie that all together. So again, next slide, we have a great example of the water energy nexus.
It's almost like we coordinated this, Amy.
Almost like.
This example, we were brought in kind of as another professional services firm did the design on it. We were brought in as a professional peer reviewer because they were looking for some incentive, and they were putting together multiple pieces kind of in a public-private partnership aspect, and they were able to get, this project is actually in process of construction right now. They were actually able to get some local state-based funding and some local municipal funding. The challenge they had was this project was contemplating some exterior LED lighting installations where they didn't necessarily have a lot of infrastructure already in place. So they were new lighting loads on the grid. And then also it was fairly close to and adjacent to a residential or a water pumping station that served a residential neighborhood. So then, one of the, common pushbacks in solar is, hey, it doesn't really do anything for us when the sun goes down, right? Well, not necessarily, because when it's part of a microgrid, you have the ability for battery storage, as Amy has mentioned a couple of times, some smart controls. And in this case, well, exterior lighting gets lit up at nighttime. Residential water use is a little bit more irregular than some loads that are controlled. And also it's heavier at nighttime and not necessarily consistent. So this was an example of where a microgrid is able to solve that unique but steady load situation. And then also the adoption of some smart controls. It's able to solve their problem. They wanted the infrastructure of some new exterior lighting to light up a park and an area in the community. And then also they're able to control the pumping station, or control the load from the pumping station with that solar and battery in the controls. So this is kind of connecting a few of those dots with some of the information Amy has shared to this point. So Amy, keep going with the good knowledge.
Awesome. So next from our components chart, we had renewable generation. I've already mentioned most of these. Solar PV is kind of the most common, and we'll dig down into the details of what that looks like. Wind is also out there in the mix. What I will tell you is that for cost benefit purposes, we typically don't look at wind until we have a relatively large load to serve. For small loads, solar PV is much more cost effective. And so for small facilities, we're not often looking at small wind turbines, especially if the cost effectiveness, the economic return of the project is a priority. If it is more of like a science experiment, sure, we can do some small wind, but generally wind doesn't pencil very well until it's large. So we're looking at large industrial or communities. Definitely, hydroelectric tends to occur in very specific geographic conditions. I've worked with a lot of hydro in the Pacific Northwest. And then we also would be remiss if we didn't talk about the heat side. So solar thermal for heat, where you have panels that are collecting energy and then using it to heat water or heat other substances to then transfer into be used inside, is very common all over the world, except for in the US. When you go to other countries, you will see people with their hot water up on the roof getting warmed by the sun. And so we'd love to see more of that happening, specifically to be used as a heat resource. Geothermal is also taking off in terms of a heat source where you're drilling down and you're using heat from the earth to provide heat. Heat from the earth can also be used to then generate electricity, again, in that exchange between heat energy and electrical energy. Next slide. We'll talk about the energy storage options at the same time, because like I said at the beginning in the topology section, renewable generation is often not dispatchable. That means you don't get to decide when it's on or when it's off. Solar produces when the sun shines, wind produces when wind blows, etc. Even hydro is dependent upon the flow rate in the water that you're accessing, which can be affected by water tables, drought years, snowpack, all of those things. So energy storage allows us to mitigate some of that intermittency that comes from having non-dispatchable resources, takes our non-dispatchable resources and makes them dispatchable. It also can provide, through their inverters, it can provide other services that provide stability to either the local microgrid or even the larger utility grid, like frequency regulation and voltage stability. What's important to a lot of people when they think about batteries, you're thinking about like what's in your phone. And indeed, the rise of lithium ion batteries and the reason that we use them for so many applications came from the personal electronics revolution. The lithium ion batteries were developed to be more energy dense and have a much larger cycle life than previous alkaline batteries, zinc batteries, lead batteries, and to be also lightweight and portable, speaking of lead batteries. And for those reasons, the energy density, the cycle life, and the portability of them, lithium ion has become the dominant chemistry of batteries because of those performance characteristics. But it's not the only show in town. I've already listed some chemistries here. Nickel metal hydride is actually very old chemistry. It's been, as Michael mentioned, I come from the aerospace industry. Nickel metal hydride has been used in aerospace applications for years and years and years, and is very stable. It's just slightly less energy dense than lithium. Lead acid are the batteries from your car. It's very heavy, and they often are not as energy dense, but man, are they reliable and cheap. And also there's a really great domestic supply chain. We can get the raw materials for lead acid batteries right here in the United States. Flow batteries are a pretty cool technology that involves a liquid electrolyte that gets pumped back and forth and then charged or discharged as it's pumped between tanks. And so the apparatus to charge the battery and extract the charge from the battery is quite expensive. But once you have that, adding tank and adding liquid electrolyte is very cheap. And so you can get a lot of capacity in your battery once you've made the investment in that mechanism. There's also lots of work being done now that we're having this storage and microgrid revolution, lots of work being done in academia and at the labs on advanced chemistries of batteries involving other elements, focusing on recyclability and also less extractive mining processes than some of the other chemicals. We're also looking a lot at fuel cells. Fuel cells in itself, this is where you split apart water into hydrogen and oxygen, and that requires energy. So when you put energy in, it splits the molecule. And then when you want the energy back out, you let those two things come together and remake water, and then you get the energy back out. This is again, an old technology. We've been using this technology since the 1950s. But now it's come into this new era of using either water or hydrogen as storable fuels. And we think that they've been used on spacecraft, again, coming out of my world, and now are looking at like long haul trucking. How do we make long haul trucking or freight rail? And how do we supply fuel for those over, long distances? And fuel cells and hydrogen storage are coming into play. So a lot of what you're thinking, like I said, when you talk about energy storage or you talk about a battery, might be like your phone or your laptop. But when we're talking about a energy storage installation at a site, it's going to look like these pictures you're seeing on the screen. It might look like a shipping container. Large batteries can be a 40-foot shipping container or sets of 40-foot shipping containers in large battery installations. In the case of a smaller battery installation for a commercial building or a municipal building, it might be one small 20-foot shipping container or a cabinet. Fuel cells have a similar look to the battery. They're, batteries and fuel cells that are housed outside on a concrete pad. They look cabinetized. These cabinets are NEMA 3R rated, which means they're rated for all sorts of weather. Often all of these types of cabinets that are designed to sit outside will have their own HVAC system because batteries like to be very stable in temperature. They don't like to be too hot and they don't like to be too cold. So you're going to get air conditioning in the winter and air conditioning in summer and heating in the winter to keep them stable. So mostly we just want to show you here that this is kind of what you're looking at. You're looking at probably some outside space. Probably it looks like a nice clean cabinet, and these are weatherized to withstand whatever local conditions. And we have batteries deployed, from the Arizona desert to northern Wisconsin on the shores of Lake Superior to remote communities in Alaska. So they really are versatile technologies. And as we are seeing these new chemistries come out and new battery technologies come out, they're getting more and more robust to the weather. Next slide. So we spent a little time going over both different options in generation and different options for storage. But typically, if you are coming to me from a municipality and you're saying, hey, I'd like to do a multi-asset microgrid on my building, on my town hall building, on my fire station building, on my wastewater treatment plant, I'm going to start by saying, I bet you're going to want solar and battery storage. That's kind of the industry standard right now, and it's really the most cost effective. There are other technology options, but this is probably what we're looking at. So let's just give you a little bit of terminology. We already talked about the non-dispatchability of solar, that electrons flow when the sun comes out. As Michael said at the beginning of this presentation, solar is a mature technology. Again, it's been around for years and years and years in all sorts of use cases, from spacecraft down to Justin has his high school calculator on him that there you go. That's solar powered, right? And so the efficiency of our solar modules that we're installing today is so much higher than it ever has been. And we're very confident in the way that solar works and what its capabilities are. Generally, financial institutions consider it to be very low risk because it's very well understood at this point. When we take a look at your site, we're going to look to see if the solar should go on the roof. When it's on the roof, it can be a penetrating attachment, meaning screws into the roof, or ballasted attachment if your roof is flat, meaning the solar will just literally sit on the roof, and then it's often weighted down by some sandbags or blocks to keep it from moving around in the wind. Another option would be ground mount solar. Ground mount solar is typical when you have a lot of land available. Sometimes the land can be multi-use. We're seeing a rise of agrivoltaics where you can cultivate, plant the land, or graze it with livestock in between your solar panels. And that, again, is a symbiotic situation because the animals who are grazing keep the grass down so it doesn't shade your solar panel. So I have talked to people who are like in the same communities that are like, in the same county, but they're like towns next to each other. And one community will say, oh my gosh, I think rooftop solar is really, really ugly. I would never do that to a building. I only ever want ground mount. And then the people in the next town over will say, I hate ground mount solar. It disrupts the sight line, only ever roof mount. So this is a personal preference. This is aesthetic, right? And so we don't really have a recommendation for you of like what's better. It really depends on your site, how your site is laid out, and from the technical perspective, and then B, it is an aesthetic choice. There are a few price differences, but mostly you get to decide. What I will say is that when you do carport or awning solar, so you've seen this in parking lots where you're going to put an awning anyway to protect cars from weather, and then you can just put solar panels on top of that. If you weren't going to put an awning in the parking lot, that gets quite expensive because you have to pay for all of the foundation and all of the infrastructure that goes in to those awnings. It really is a better solution if you were going to cover the parking, but it's also an option. So those are your solar design options. When we talk about battery storage, what I want you to take away, and I have this image in your mind, is that a battery is a bucket. It's just a simple storage device. Depending on the chemistry, it works in different ways of how it stores. But a battery is a bucket, but instead of storing water, it stores energy. So we have two different design parameters when it comes to energy storage. One is called the capacity or the energy of the bucket, and that's given in electricity in kilowatt hours. That's the unit of energy. And so that's how big is your bucket. So if we look at our image here, we've got a blue pail, and then we've got a 45-gallon drum. And obviously the drum has a much larger capacity than the blue pail does, right? And so that would be the energy rating of your battery. The second metric for the size of a battery is the power. And that electrical power is given in kilowatts. So you've got kilowatts for power, kilowatt hours for energy. And power is the rate at which you can fill or empty the bucket, fill or empty the battery. So over here on the right side, we've got a little faucet and we've got a fire hose. And so you could see that even if you had your 45-gallon drum there and it's got a very big capacity, if you just put a tiny little spigot on the top of it and it can only outflow a little drip at a time, your battery will last a long time. Your 45-gallon drum will last a long time, but you aren't going to get a lot of power all at once. And so this is what we look at when we come in. And when I say we, I mean my company, Municipal, I mean Michael as a developer, I mean Justin at Energility. We are going to look at your site and look at what your power needs are. That's your instantaneous rate of consumption, and what your energy needs are. And that's how we work those two things together to pick the appropriately sized battery for you. So those decision points are: how big of a bucket do you need? What's the capacity? When do you want to fill it? And when do you want to empty it? And from our perspective at Municipal, the energy we take out of that bucket must be worth more than the energy we put into the bucket. Whether that it's worth it in a pure economic sense of dollars and cents, or it's worth it because it's backup power and it's providing continuity of operation. Those decisions about when we fill it, when we empty it, are part of the control system, which we'll talk about next, I think. Next slide. Yeah, so this slide is about control. So we need to be able to decide. Solar doesn't need a decision, really, because solar just works when it works. But now, if we have a battery and we have the ability to control when and where the energy goes, now we have to decide: are we going to use that solar energy to fill the bucket? Are we going to use it to serve the load at the site? And most importantly, are we going to take energy out of the bucket that is the battery and use it at the site? So usually the control system that does that is called an EMS, an energy management system. An energy management system is focused on your site, on the assets available at your site, and it combines what the loads, what's going on at the building. It combines what the battery can do, and it combines what's going on with your renewable generation, and then makes those decisions based on either economics or resilience, performance, and reliability to decide who's on call to deliver what energy when. The example I'm giving you here, you'll see it's called Red Cloud. This is the software that my company has developed, and we customize it for every site, depending on what the loads are, what the goals are at the site, and what the assets are available. And we operate on site locally, but then we also are getting data in from the cloud about the weather, about what's going on with the utility, and all those external sources. There are a couple of other controls pieces that I'll mention. A building management system, which is sometimes called a BMS, is one of those systems that can control and schedule your HVAC for you. Some of them are just a simple schedule. Some of them are smart and can adapt to current conditions. A good EMS that's managing the microgrid part can work together with the BMS to decide how to schedule loads. You'll also hear BMS also referring to a battery management system. That is usually a bit of software or computing that's on board the battery that helps monitor the battery's temperature and voltage and balancing between the cells. Normally, you as a facility manager will never see that. Will really never see what the BMS is doing. But again, the BMS is working with the EMS to say, hey, here's what I can do with my current conditions in the battery. The last thing I'll talk about is the last bullet here is the Distributed Energy Resource Management System, or DERMS. That is a little bit higher level type of control that can actually manage multiple sites at once. So there are reasons that you might want to do that. It could be multiple sites in a community working together to provide energy together. And so that's what a DERMS does. So we have these layers of control, and in the ideal world, they all work together. Now, at this point in the state of the industry, they don't work together by default. Again, you can't just kind of plug them in and expect it to all go together. You need system architects, you need systems engineers who are making sure that these links are in place and the right hand knows what to expect from the left hand, and they're all talking together. Next slide. I think we're going to look at our final example of a microgrid, and then we're going to open it up for some Q&A.
Great, thanks, Amy. So this last example is not necessarily a municipality, but it's a rural church, and they reached out to us because they had one massive problem. They were a small facility, but they were two issues. They were having a hard time paying their bill, and when we did the analysis, it looked like they were paying, somewhere in the neighborhood of 50 cents a kilowatt hour on average. Which anybody that knows the energy industry, in Ohio, we're anywhere from 7 to 10 cents on the kilowatt hour on the energy component. Well, they were paying about 50 cents. Well, the other issue they had was reliability. And when we started unpacking the situation, there is this church is literally here in Ohio, shocker, situated in the middle of a cornfield. They are in a small rural community, and they have an all-electric building. So they were trying to figure out, how do we get a natural gas pipeline so we can get a natural gas generator? Well, once we started talking to them and we understood, this goes back to Amy's very beginning introduction of level setting, is with the electric system that they have in this small building, they have two large electric furnaces. And so they're consuming between 15 and 30 kW on an instantaneous moment when the weather is really cold. And because of the way the utility rates are structured, is that demand, that instantaneous demand, they're paying for the other 11 months, they're paying at least 60% of that demand charge, regardless of whether it's a cool spring season or a cool fall season, and they barely run the lights and air conditioning. So they had two issues, reliability and then also the extremely high cost. So they're in the discernment right now of trying to put in what would be a small microgrid. And it goes back to Amy's point of, we have all these components that go into making a microgrid technology possible, but the simplest format is solar, batteries, and some sort of control. So they're looking at ways to be able to be reliable and keep the lights on and the doors open, but at the same time being able to afford to keep the lights on and the doors open. And this is a potential for them, because the alternative is going many, many miles through rural area to get to the natural gas pipeline to get what they thought they wanted initially. So again, it's a technology with solar that's been around for a while, battery that's continuing to evolve, and they're looking at this for a couple of different reasons, to be able to stabilize finances. And then as a church, they're looking at theologically, we don't necessarily want to trench up the ground and pull gas out of the ground and fossil fuel based heating, but we didn't know that there was another option. So again, these examples we've provided to augment Amy's great explanations in the technology are just a few of the ways that this technology can be bolted together, either in small or large format, either in disaggregated territories or with unique loads. And so, appreciate the opportunity to share these examples with you. And I think, Michael or Rachel, you're going to take it for some Q&A. And we got a little time to answer your questions.
The timing has been perfect with our speakers today. We are 10 minutes till 2. We don't want to waste anybody's time, but I do not see, unless I missed it, I don't see any Q&A specifically in the chat. I'm going to wait a few seconds just to see if something pops up. And then if anybody wants to raise a hand, you can do that. Otherwise, I do have a few things I'm going to add because, of course, I always have something to add. All right. Well, one, thank you very much to our speakers. I do. So there we go. Have you seen any innovative solutions with House Bill 15? Okay, so one of the reasons that this whole series exists is because of House Bill 15. So let me do an overview just real quick for folks who don't know. House Bill 15 has unlocked a lot of, there was a lot of things into it to modernize our energy grid. But one of those things is to be able to have and operate distributed energy resources behind the meter. What that means is you would design your energy system or microgrid for your facility behind your electric meter for you. And then, of course, you can have energy sent back and forth through that meter. If it's bidirectional, of course, what you do put together would be new and would be bidirectional. So yes, House Bill 15 has unlocked the possibility of all of what we talked about today. And that's what's so useful and beneficial in Ohio. Before that, it would have been very difficult to do. So it really has been a big improvement. And now the innovative solutions are starting to come out. But one of the things I want to emphasize, since we have a few more minutes, is what most folks don't realize is our electric grid is analog. So those of us who remember records, vinyl records, or actually people are now collecting them again. To choose a track on a vinyl record, you had to physically pick up a device with a needle and put it down in the right spot, or flip the record over by hand. And then it would play the music and it was analog, not digital at all. But most folks today have everything operating on digital. The stuff that we're talking about is all digital. So to use digital technology in Ohio, House Bill 15 helped make that possible. What we need to make the electric grid to do is it also needs to become digital. So Amy kind of touched on all that when she talked about the controls and the different levels, but really we are changing the world of energy. It's always been analog and it's now going to completely switch. And for those of us who are old enough to remember the corded phone hanging on the wall or sitting on a desk attached to a piece of copper, that's what we have currently with our electric grid. And we're going to be going to not just cordless phones, but all the way to cellular phones and IP-based devices. Go ahead, Amy.
So I'll just add on to what Michael said to give you, so I do work in the state of Ohio, but we also work all across the US. And what I will tell you is that HB 15 is actually quite revolutionary. It's quite innovative. Many times, community level microgrids or multi-parcel microgrids are forbidden for policy reasons and in the regulatory environment. And so there actually hasn't been a lot of work done from the technical perspective to solve the innovation challenges of that level of complexity and that level of control. I can tell you from my perspective as a systems engineer, I'm very excited to see this type of work develop. But I want to remind everyone who is interested in doing things. I see Joyce asked a question about vacant land parcels near a commercial industrial center, that all of this is, when we do these projects, it's going to be innovative. They are going to be the first ones, and it will be exciting, but it will also have its challenges. And we all just need to go in with our eyes wide open to say, we're willing to be the pioneers at this. and figure it out. And from, again, my perspective as a technologist, that's super cool.
Yeah, I got into this. I'm a retired fire chief, so I got into this when I retired from that world, seeing that electrification was coming, especially to municipalities. And it really is like those of us who remember the space age technologies coming through and how those things happened. Uh, but it's crazy to see what's happened in other technologies that are coming into this. Somebody asked the question, did AI data centers move the House Bill 15? I would have to assume that the future demand or expectations of higher demands on the grid, and data centers are one of those things. Probably the biggest one at the moment, was something that would help move House Bill 15. But the benefit for all of us is what they might need in capacity from the grid, we can help provide, but also get paid for and be able to use it by building the microgrids for ourselves that also work with the electric grid and get you benefits. So we talked about that in the stacking value session, that not only can you get value for yourself, but you can also sell your excess energy to get revenue for your community. So really is a good thing. As far as we're concerned, House Bill 15 is a very positive thing for the state of Ohio. Go ahead, Justin. We got about 2 minutes.
Yeah, I think with the and that was a great question, because one of the things that we've always said is follow the money. And if the tech companies are putting billions of dollars into data centers, and then they're also trusting it with, we believe we can have this stable off the grid technology, then that means it's not cutting edge. Just the adoption of it is more cutting edge. And so while it might be driving some of the conversation, it's certainly, to Amy's point, gonna seem revolutionary as municipalities and smaller entities adopt what is more tried and true technology in a unique format and fashion.
There's one
So
last question. Oh, go ahead, Amy.
I was going to say, let me really quickly, I want to say Joyce's question about developing a microgrid system and Matt's question about tools, like Michael said in the chat, come to our next session about the development process. We'll talk about those things. But I want to get to Julie's question in the chat about these projects are behind the meter. What needs to happen to drive dispatch at an ISO level? This is actually, so what we usually say here at Mugrid is that the utilities should be aligning their rate tariff with the behavior they want to see. They should be incentivizing, and that's true. The ISO and the large scale T&D should be setting up the market so that the utilities are responding in a way that is healthy for the whole system. That's why we have real-time spot prices, right, out on the wholesale market. So the market, this is how capitalism should work, right? The market should be driving the behavior that is beneficial to the network. And then from there, the distribution utilities should be structuring their rate tariffs and their rate programs to individual consumers and sites to drive the behavior they want to see that is also beneficial to both the distribution level of the network and the higher levels of transmission. And if we trust that that is occurring, then our behind the meter resources that are small 20 kilowatt units, should be incentivized to do the right thing from behind the meter. It doesn't always work that way. And for a very long time, the rate structures and the way that utilities and ISOs operate kind of in a vacuum separated from the customer has been to promote stability at all costs, reliability at all costs. And so now that we're seeing this shift to behind the meter, then we're going to see also, I think we're going to see an adaptation of the way the market dynamics are passed to the consumer. And hopefully that's the way we look at it right now. We look at it that the behind the meter systems do benefit the grid because they're responding to the rate tariff.
All right, folks.
I could talk about that for like 2 hours.
Yeah, it's a whole other session. The last two questions, I'll throw something together real quick, since we have 60 seconds. The feeding into the transmission and the behind the meter and putting them together, that's exactly what we're talking about. Let's build all of these microgrids, and this series is specific for municipalities, build all these microgrids and operate them now. House Bill 15 lets us do this as a virtual power plant. So now when you have one physical utility with, or one physical facility with 2 megawatt hours of storage and a megawatt of power rating, now that's available because it's designed for your worst day. But on your good days, you can sell back into the grid, which is 99% of the time. So yes, we're doing exactly that, trying to take small things, put them all together, make them big, and now we've got a nice virtual power plant, or what we call a distributed power plant in Ohio, and that's Green Energy Ohio's goal. So now that we are at the end of time, the next session you will see Amy again. It will probably be a lot of Amy, which is just fine. I love Amy to death. And she's going to cover the process of how we design microgrids, the engineering, the feasibility assessment before you get started, and of course how to make it actually happen and work the way it's supposed to work. One of the key things people don't realize, you can buy a turnkey solution. It may not do what you want it to do. So you got to make sure it's designed and operated properly. The next session will be financing, and maybe I'll have to ask Justin if he wants to come back and join that group. So that'll be 2 weeks, so 4 weeks from now, 2 weeks later. And then the last session will be where we put it all together. We're going to be talking about this energy transition that we just touched on today. We're going to get some lessons learned from North Carolina, where they had Hurricane Helene and they did not have the microgrids that they wanted, but they're spending money to build them now, which is a great lesson to learn. Learn the lesson before it happens to you. And lastly, this graphic I just wanted to share. This is really a century of evolution. Internal combustion engine vehicles have been worked on and modernized and made as efficient as they possibly can, and they're never going to get above 40%. And it's been 100 years they've been doing that. But the same technologies we want to use today have also been getting better and better and better over time. But now they're all coming together because they are economic and they're the right type of technology and they're mature. And it's now time for the energy systems that we want to have that are digital and smart and based on electricity, not based on fossil fuels. So we will see you in 2 weeks. We went 1 minute over. My apologies. Everyone have a great week. Welcome to the nice, balmy, warm weather in Ohio. We're above 20. Woohoo! On the way to above 30. So have a great week, everyone. We will see you later.